Now, in this segment, we'll look at relational algebra operations for different kinds of join. And along the way, we'll introduce two new join terms, theta join and natural join. Joins and Cartesian products are expressed via three new relational algebra operators to go with the already introduced pi for projection and sigma for selection operators. First, RA uses the symbol cross, or x, for Cartesian product. So the Cartesian product, or unconstrained join, of two relations R and S is written R times S. Now, RA uses the symbol this, usually called bow tie, although we'll just call it join. So it uses the symbol join for a constrained join, with the condition of the join as a subscript. So a join on R and S with primary key R.ID set equal to foreign key S.RID would be written thus. The SQL equivalent, just to be clear, would be select star from R join S on R.ID equals S.RID. Now, a constrained join is also theoretically termed a theta join. And that's a term commonly used for such joins in theoretical discussions, so be sure you're familiar with it. It's just another term for inner join with a condition. A three-table theta join can be viewed as a two-table theta join whose result, so start with a two-table one there, two-table join there, whose result is in turn joined with a third table. So the multi-table join is represented as a series of bow tie or join operations. Join operators associate left to right, just like multiplication operators do in arithmetical algebra. So the implied parentheses here are there, like that. Now, question one here, just to be sure it's clear and to get in practice for what will be a recurring theme, please write the select statements that are the SQL equivalent of these join operations. This one here and that one there. And what you should have come up with for that is select star from customer, join receipt on customer.id equals customer ID. And for the second one, relatively longer, break that up a little bit. A select star from receipt, join line item on receipt ID equal receipt ID, and then join product on product ID equals product.id. Okay. Now, try adding the other two operators we already know to translate this rather larger expression into SQL. And what you should come up with there is, so we have the two joins, and then a where clause to implement the selection, and then of course a choice of column receipt ID to implement the projection. Now, there are several points of note in this answer. First, RA operators can be combined in arbitrary ways, just like operators in any other kind of algebra. So we can perform joins on the results of other joins, perform selections and projections in turn on the results of the joins or other operators, and so forth. And the second point is, did you get the distinct in your answer? The first two queries that we did produce no duplicate rows, no duplicate tuples, but the third does, since multiple line items may match the same receipt. So relational algebra expressions return relations, again, sets with no duplicate tuples, and well-designed SQL queries almost always do too. Indeed, one could make a convincing argument that the distinct keyword is a misdesign in the SQL language. Distinctness should have been assumed, with some keywords, like maybe all, for the cases where duplicate rows are actually desired. Remember to include distinct in any SQL query that is meant to implement a relational algebra expression if the query might produce duplicate rows. In fact, by the way, the reason SQL requires you to specify distinct is that it's an expensive operation. and so it should not be a default. Distinct slows down the query implementation considerably, since it requires some sort of sorting to put common result rows next to each other for elimination. And as we saw in earlier topics, some SQL queries do assume the distinct, often because they had to sort the rows anyway for other reasons. And in those cases, you get duplicates via the explicit keyword all. So SQL actually does assume the set relational interpretation when efficiency permits it to, and also lets you require it, even at extra cost, by adding the keyword distinct. Now, let's talk a little bit more about the join on versus comma-separated table syntax for joins and how that relates to relational algebra. Many SQL writers would say that join on is the true syntax for joins, and that the comma-separated table join syntax, which we've discussed in earlier lectures, is kind of the alternate. It's really a matter of taste. As we said earlier, you should be comfortable with either syntax, but the join on syntax more clearly matches the relational algebra by putting the join and its condition together. And it can express some different types of join operations that we'll encounter soon. Now, let's look a bit more at those two SQL syntaxes and the relational algebra operators bow tie and cross for Cartesian product. So question 4, just as a reminder of comma-separated syntax, try writing the two SQL statements right here, the two selects, without using bow tie operators. So select star from customer and receipt, and select star from customer and receipt where receipt ID equals ID. And the answer is pretty direct here. What we're going to do is use customer cross receipt. Remember, that's simply a Cartesian product, so it translates to a X operator. And then we could write the other as the selection operator, receipt ID equals ID, on the Cartesian product. So a join can be rephrased as a Cartesian product with the join condition applied via a selection operation. And these two representations of joins in relational algebra are reflected in the two SQL choices between join on syntax and comma-separated table syntax. So here's a brief table summarizing the analogies, with the last two rows being two ways to express the same thing, really. So cross product of R by X is select star from RS. A selection on some condition on that is select star from RS where condition C, or alternatively a bow tie with a condition on it is the analogy to a select star from R join S on C. Now, if a join is just a constrained Cartesian product, then can we write customer X receipt as customer bow tie receipt without a join condition? Does this by itself without a condition mean the same thing as the X? It would make sense, but it turns out that the bow tie symbol without a condition is reserved instead to represent something called a natural join. The natural join is a join where the condition is automatically an equality between all same named attributes of the two relations. So let's say we have two relations, person with attributes social security number, age, and gender, and then tax return. These represent a one-to-n relationship between person and tax return, with the foreign key tax return social security number referring to the primary key SSN in person. One person may have many tax returns, right, for many years. If the foreign key in one relation has the same name as the primary key in the other relation, or the same names if the primary key and foreign key are multi-attribute, then a natural join implicitly uses those name-matched attributes for its join condition. In other words, this person natural join tax return is the same as saying person join on the match of the social security numbers tax return. And if several same-named attributes exist, then a natural join requires that all of them be equal. Let's say we augment the social security primary key with attributes first name and last name in person 2, in an effort to compensate for the fact that social security numbers get reused on death. And then we'll have tax return 2 likewise. So the foreign key and primary key are now multi-attribute. And the natural join between the two now translates to person 2 join with all of that condition, all of the same named attributes matching on tax return 2. Many theoretical database discussions assume same-named primary and foreign keys, so a natural join is a useful shorthand in such discussions. It's much less common for tables in a production database to have same-named primary and foreign keys, since the use of machine-generated ID columns is pretty common, and that necessitates names like customer ID for foreign keys to avoid clashing with the table's own primary key ID. Still, MySQL and other DBMSs do offer a syntax for natural joins, though it is actually not SQL standard, and it's this right here. In MySQL, the natural join that we've been discussing here above would be written as select star from person natural join tax return. We did see one practical use for natural join, by the way, when linking person, teacher, and student tables in the courses database. There, the join condition matched IDs from both tables and could have been done as a natural join. And then finally, what about outer join? Well, RA uses the following symbols for the various forms of outer join. For left outer join, we get either a bow tie with little L subscript, or this funny looking bow tie with the arms on the side that is not going to be nulled. For right outer join, an R subscript, or again the little arms on the side that will not be nulled. And then just to be complete, a full outer join has a bow tie with arms on both sides like that. So a final question 4 here. With that in mind, write the SQL that I just added here to the notes in RA notation. So this SQL statement right here. And you should come up with it kind of working from the inside out. We'll do a left join with that little L subscript, or you could again have used the one with the arms on it, and the condition between product and line item. Selection condition for product ID being null after that, and then finally the projection or select of flavor and kind.